Hello, everyone. I hope everyone is safe. So, my name is Amel Sellami, and I'm an GDE in machine learning. I'm a research engineer at Anstabib, and you can find my Twitter handler below. It's Diplernosa. So, before diving into our presentation of the day, let's talk about the initiative that Google is hosting. As we can see, we have 16 weeks of pure online community with various topics ranging from machine learning, design thinking, Flutter, Firebase, Kotlin, Android, and so on and so forth. One on the best part is that it's hosted by different people across the region from UAE, Algeria, Morocco, Tunisia, Palestine, everywhere. And it's actually in three different languages. So we have French, Arabic, and English. So today is the last session for today's session. And if you're interested to know more about this initiative, please join us and check the links like digital stream, digital website, and digital feedback. So how about let's dive? So now let's dive in our pots, which is the topic of our topic today is computer vision demystified. So, but before this, there are two more things that we need to mention is like, if you want to have an attendance certificate, you can go like in the MENA digital feedback, and you can get like a win special gift box if you solve 5 quests between March and June. So, first things first, for what is artificial intelligence? So, machines that mimics human intelligence are called artificial intelligence. So the theory and development of computer systems able to perform tasks normally require humans' intelligence, such as visual perception, decision making, translation between languages, and so on and so forth. After defining what is artificial intelligence, let's talk about there are two types of it actually. The first one is AGI, which is artificial general intelligence, the intelligence of machines that has the capacity to learn any intellectual task that a human can do. And in AI, or simply artificial narrow intelligence, which is machines that only solve a specific task, like smart speakers or self-driving cars, right? So another things that I wanted to talk about is the difference between artificial intelligence, machine learning, deep learning, and data science, because I get this question very often. And as you can see in the picture, there is an intersection between artificial intelligence and data science. So data science is actually scientific, like scientific methods like algorithms and systems to extract knowledge or insights from big data. Whereas deep learning, which is a technique from implementing machine learning like self-driving cars, in which neural networks adapt and learn from vast amount of data. Deep learning is included in machine learning, which is by definition the ability to learn without being explicitly programmed. ML in itself is included in AI, in artificial intelligence, which is defined by human intelligence exhibited by machines. So, but as you can see, there is lots of research area in artificial intelligence. That's why machine learning and artificial intelligence are not. That's why machine learning is included in artificial intelligence. As you can see, like there is rule-based reasoning, machine learning, NLP, autonomous vehicles, and so on and so forth. So before going on, the difference between machine learning and deep learning as it is, simply put, is that you have an input at the same base level, but and you get an output, but the different way of having your model is not the same. So in machine learning, you have your feature extraction and classification, two different things apart. But in deep learning, feature extraction and classification are the same. So it's like combined together. So So this is basically the difference between machine learning and deep learning. So we're talking about deep learning, but why are we talking about it right now? One of the things that we must know is that everyone right now has a smartphone, right? So the data is very massive. We have data everywhere in smartphones, in smart homes, everywhere. So it's a lot more easier to do deep learning with this. And of course, let's not all forget the hardware industry, like getting more and more complex and giving better and better results. So with combination, when combining massive data, hardware, and deep learning, you can achieve tremendous results. Okay, now let's dive in the machine learning types. Okay, so when we talk about machine learning, there are three types of it, which are unsupervised, supervised, and reinforcement learning, as you can see in the picture. So unsupervised learning uses unlabeled data. So basically using different models try to find similarities in the data, as you can see, for example, in clustering example. So you have your data, and this data you're trying to cluster the similarities, the data that are similar in the whole bunch of data. Whereas supervised learning task of learning a function that maps an input into an output based on an example, input-output pair. And well, supervised learning, we can use it like, for example, for classification or regression tasks. And reinforcement learning concerned with how agents out there to take the actions in an environment in order to maximize the notion of cumulative reward they have. And this is a branch in itself. Okay, now we're going to something really interesting, which is machine learning workflow. And what is the typical machine learning workflow? As you can see, you get the data, you clean, you prepare, and manipulate your data, you train your model, and you test, and then you improve. Well, test your data, then you evaluate, and then you improve. So let's try to dive a little bit into them. So, for example, when if you want to get the data, well, it could be available in, like, for example, Kaggle, Zindi, or any other platform. You can even there is also a Google dataset search that can help you find the dataset that you are looking for. First step, clean, prepare the data in a typical computer vision task. Images cannot in a good resolution, so one thing to do is to clean your data and import things to remember. And one thing to remember also is to add data augmentation. Data augmentation could be like flip, rotation, and every like translation or anything. So to the data set, so that that your model can generalize well on your data and do not stick to a certain form of your data. Third step is to train the model, but a very legitimate question here is what model should I use, right? Well, in a typical computer vision task, you would probably want to try the state of the art algorithm. For example, in an object detection task that we will talk about later, is that the detection task, the state, you can see the state of the art one. For example, here we have the Cascade, Mask RCNN, or the Efficient Det, which is developed by Google. You can try first these kind of algorithms and then try to do hyperparameters tuning or everything after you start these state-of-the-art algorithms. So after choosing our model, now we're going to train it, and train it is basically going to need to train it, and then we're going to need to test it on the data that the model didn't see before. Then we need to evaluate our model. The best part is to know whether your model did generalize or not. And how are we going to know that? So to evaluate our model, we need to calculate the accuracy for the training and for the testing. So if the accuracy of the model while the training is low and the model is unable to learn. But if the accuracy of the model of the training is good, but the testing is bad, the model is unable to generalize and is overfitting to the training data. So the first case scenario is what we call underfitting. The second one is what we call overfitting. So here, depending on our case, we're going to improve our results. If you have like underfitting, which is the case that the model is unable to learn, then we might want to add some data or perhaps adding complexity. And we might add some, if you say, for example, I don't have data, Well, it means that, for example, you can do data augmentation on them and add some data on for your model. You can add also complexity to the model. So this is in a case if you're having underfitting, but if in case you have overfitting, which is the case that the model is learning by heart, memorizing and not generalizing through the data, then we might want to add some regularization techniques like dropout, L1, L2, or even change the optimization. Bottom line, changing the hyperparameters of your model. And this is what we call in like machine learning and everything hyperparameter tuning. So we want to change all these kind of things to have a better model and a better results. Now, after seeing the workflow, I wanted to talk about the computation hardware. So we talked about the massive data is important. Hardware also is important because computation hardware accelerates the process of training and then testing your machine learning model. So if you're having, for as a comparison, consider this, for example, you have a CPU which can handle tens of operations per cycle, whereas a GPU can handle tens of thousands of operations per cycle. A TPU in itself can handle up to 128,000 operations per cycle. And as you can see, CPU, like small models, small data sets, useful for design space exploration. A GPU, medium to large models, data sets, image video processing, application on CUDA or OpenCL. And a TPU, you can use matrix computations, dense vector processing, but unfortunately, no custom TensorFlow operations for now. And if you want to see, this is like a typical CPU-based, GPU-based, CPU kind of things. It's like a hardware, but hardware changes and it drastically changes the results and the speed of the results. Because if you have a very fast model, you can like test different models and choose from the best. But if you don't have a very fast model, you're going to try intuitively find the best model and or the one that the research paper said that is the best and try it because you don't have enough GPU or TPUs in your computer or in what you're doing. Okay, so I wanted just to add these learning resources before getting into computer vision directly. So one of the things that people, beginners, especially in machine learning, deep learning, or anything, use or learn from are the deep learning from Ian Goodfellow, the deep learning book, which is very popular, An Introduction from Saturn. There is also the Deep Learning Without a PhD by Martin Gorner, who works at Google, which is really useful, especially for computer vision. It's on YouTube, it's free. And there are online classes like Coursera, Udacity, uh, deeplearning.ai, and there is also fast.ai. There is also Kaggle and Zenji if you're interested more about challenges and competitions. And if you say, for example, I don't have money or anything, you can even like apply for scholarships or financial aid with Udacity or Coursera. Great. Okay, now we're going to the best part, the fun part, which is computer vision. Well, actually, if you want a machine to think, teach it how to see. This is what Li Fifi said before. And I think it's very important to know that teaching someone is by seeing is very important. So we've been talking about we've talked about computer vision, but here are some applications of it. So the first one is there are lots of applications in computer vision, but I choose two of the most important ones, which are healthcare and then security. If you're seeing here, we can even detect diabetes from the retina using computer vision, which is really phenomenal, or pneumonia you can do this with computer vision tasks or tasks like like object detection or image semantic segmentation. Another interesting application about from the healthcare is security. For example, whether in shops or roads or any other place, you can like detect if someone is going to do a thief or rape a woman or any other kind of application that you can use using cameras and video surveillance. So we've been talking a lot about computer vision, but what is computer vision? Well, computer vision is a field that deals with how computers can be made to gain high level understanding from digital images or videos, right? So, and actually, computer vision has four main tasks. The first one is image classification, object detection, semantic segmentation, and then instance segmentation. We'll dive indeed into details in these four, but first, let's start with the image classification. Image classification is the network tells if the image contains a specific object or not. For example, if there is a dog, a cat, or anything else in the image, right? If you're going to classify your images, you have like a bunch of images and you want like a small classifier for them, right? Then after after uh, image classification, we have what's called object detection. Object detection is detects object within an image. Like you can see here, you have buildings, humans, bicycle, or the kind of objects that exist in an image. Well, and it depends actually on the object that you want to detect. For example, if in an image you want to detect every object, that's very feasible. But again, and then you would need lots of data sets. But again, if you have a very specific task, like for example, detecting buildings or detecting humans, or for example, to count them or to do anything with them, it's very feasible also. The third one is semantic segmentation. Well, in semantic segmentation, the network assigns a class for each pixel. As you can see, each object is colored to showcase the class it belongs to. So as you can see, we have like humans in red, cars in blue, and the road is like, or the trees in green, right? And and the last one is instance segmentation. So instance segmentation, the network detects the objects, then provides the semantic segmentation for each one of them. So this is the difference between semantic and instance segmentation. As you can see, we have for detecting images and we're detecting like the chairs. In a semantic segmentation kind of task, all of the chairs will have the same color, which is blue. But in instance segmentation, you will have like chairs which are colored in red, blue, purple, green, and every possible one. So these are the four tasks of a computer vision. And again, image classification, object detection, semantic segmentation, and instance segmentation. This is a kind of recapitulation of the four kind of tasks. As you can see, we have like balloons for classification. We want to detect the objects. And then the difference between the semantic and the instance segmentation is the colorization of the balloons that exist in the image. So basically, these are the most important tasks or the computer vision tasks. Okay, so now let's go to the fun part. How does a computer sees an image, right? So an image is represented by a matrix in a computer, and each image is an array of pixels. So if you see all these numbers are the pixels of an image, and these pixels are ranging from 0 to 255. And these values represent white, shade of gray, and black. So every image is represented in these kind of pixels. And a pixel a signs like a signal or an activation. If it's activated, it's going to have a signal. If it's not activated, it does not have a signal. But all the images are not only in grayscale, right? So images are in blue, green, are colored. And these colors are basically using RGB, which is red, green, and blue channels. So R stands for red, G stands for green, and blue, B stands for blue. So every color, you can mix every color to find the color that you want. All these three to find the color that you want. So we have a matrix which has pixels, values, and each pixel has a value of R, G, and B, like red, green, and blue. Okay. So is it a cat or a dog, right? Basically, this is an output. What is the process? How an image, after seeing these kind of things about an image, how a neural network understands if it's a cat or if it's a dog. So basically, we have these images, and these images, we feed them to our network so that we get an output of a result of our computation. But how it is done, right? So one of this is that it's very popular in computer vision. One way to do this is called CNNs, which are convolutional neural networks. You might want to ask why these CNNs are very popular and very powerful. Well, because images are spatial, right? They're represented in a spatial way in the space, and convolution works pretty well on them. Which is a convolution is actually mathematical operation, and it generally tends to give great results in these kind of tasks. Great. So, okay, but how all of this makes sense for numerical numbers, right? So we have the numbers. The process is called feature extraction. We're going to extract features, the representation that represent the data at first, and feature could be called contours, edges, etc. These features are the key description of an image, which are used as data to be sent in machine learning algorithms for further creation of hypothesis functions, again, models, which then can be tested. Deep learning simply simplifies the process of feature extraction with convolution. Great. Okay, thank you. But what is a convolution, right? So a convolution is a mathematical operation which maps out an energy function, which is a measure of similarity between two signals, or in our case, image. Okay, this is great, but intuitively, what is it, right? So you can start with the kernel, which is simply a simple matrix of weights. We have this is our matrix, which is our image, and we have the kernel, which is the weights, and then this kernel slides over the images, which is our input, performing an element-wise multiplication with the part of the input, which is like element-wise multiplication, right? And then after this element-wise multiplication, you sum it up, and the result you get a signal output pixel. So the result is convolved image. Well, you might ask, what is this process if an image is an RGB? Actually, it's the same way. It's like you're having your kernel, you're having your matrix, and then you do a element-wise multiplication, and then summing up together to get the result that you want. So this is the result of our convolution. So the most important part. Okay, so the most important part is that in convolutional neural networks, there is a convolution, which is very important to have the features extracted. And this is typically a result of our convolution. So as you can see, you have your image, which is like basically trees, and after convolution, you get all the signals and activations that you want to have from your image. So we have a convolution, but CNN does not include only convolutions. We have also something called pooling layers. And a pooling layer is actually uh, downsampling of the image. You downsample your image. For example, there are two types of pooling layers. You have max pooling or average pooling, or perhaps other types. But the most important ones are max pooling. And the max pool is just takes, for example, from a multiplied by two filters and a stride of two, you get the max out in each rectangle. For example, here we have the number 6, here we have the number 8, here we have the number 3, and here again we have the number 4. So after a convolution, we do a pooling layer. All these two creates a better understanding for an image so that we can have a result. And a typical CNN example architecture is this. You have input data, convolution, you have your feature maps, you do pooling, you get your feature maps again, you have a convolution, and then you do a linear classifier to get the objects and the categories of the objects that you want to get. But you might want to ask, perhaps I should get back, is that why we're using pooling layer, why we are reducing the dimensionality. One problem is that the output feature map that we've talked about from this one, which is like this output feature map can tend to be very sensitive to the location of the features in the input. So one approach to address this sensibility is to downsample the feature using pooling layers. This is why we're using pooling layers after all. But well, typically this is a CNN example architecture, right? And basically what we do in computer vision, we use all these blocks like a convolution layer, a pooling layer, and then of course an activation layer. It can be generally used using rectified linear ReLU. Rectified linear ReLU. Okay, I think the sound is not that clear. I might be wrong, but yeah. So okay, so as I was saying, CNN is like convolutions are the main part of the convolution neural networks. It's like you're having a block. You're having a block of you have a CNN pooling layer, and then you have your activation. And the activation generally we use rectified linear units, which are very popular nowadays. And then this block you can repeat it like twice, 3 times, or even more to do like to extract features from your image. And it depending on your image, if your image is very complex or very that has very object in it, or it does not have very object in it. So it depends on the image after all, and it depends on the complexity of your model and the things and your data that you want to do with your data. Okay, so basically this is all for I tried to sum up all the important things about a computer vision, which are the tasks and how convolutions and pooling layers works, but there are other important things that you can learn and look in. For example, in papers with codes, you can have like all the best paper, state of the art papers for a specific task. It could be semantic segmentation, object detection. It could be also NLP or even reinforcement learning. So apart from this, I wanted also to share with you, to show you an example, a very typical example on how to do this. And if you have questions, please put them in the section in the chat so that I can answer them later. So here's a very specific classification. This classification is classifying images of clothes, and this is done by TensorFlow. So you can find it at tensorflow.org. There are lots of amazing tutorials there that you can start if you're a beginner. And the first thing is that we have here, we're going to have a TensorFlow, we're going to use TensorFlow 2.x. So the last version of TensorFlow. And first of all, we're going to import the libraries like TensorFlow, Matplotlib, NumPy. And we're going to import the fashion MNIST dataset. So this tutorial is like based on fashion MNIST dataset, which is a very popular dataset. It's available online. It's free, and the goal of our tutorial today is to do a very simple classification. So this guide uses the fashion MNIST dataset, which contains 70,000 grayscale images in 10 categories. As you can see, there are different categories in here. We have like shoes, dresses, coats, pullovers, and so on and so forth. And each image is a 28 by 28 pixel, as you can see. So first of all, what we are going to do is going to import our dataset, which is fashion MNIST. It's like you can have it from Keras dataset fashion MNIST. Keras, well, TensorFlow 2.0 uses Keras and also an estimator as their APIs. No more TIFF slims, no more contributor, because in TensorFlow 1 it was very messy in a way, and in TensorFlow 2 it's like very clear on which one you can use to build a model in TensorFlow. So train images, and then you're going to split the images in train images, of course, train labels, and then the test images and test labels. So we're going to load the dataset from Keras. It's very available again online. And as you can see here, we have like 10 classes from 0 to 9. We have t-shirts, trousers, pullover, dresses, coats, sandals, shirts, every possible one. And first thing, we're going to put all these in our class names. Then we're going to explore the data. As you can see, we have like 60,000 train data, and each image is 28 by 28 pixels, right? So the train labels, as you can see, for example, the first image is labeled 9, which is a simple category. There are 10,000 images in the test dataset. So here we have 10,000, 28 by 28. So again, we have 70,000 images. We split the data to 60,000 and 10,000. 60,000 for train and 10,000 for test. First thing is to process the data. So this is the data. As you can see, I was talking about the activation signal of a pixel, for example. As you can see here, these are the activated pixels. And as you can see, the shape of them, this looks like a boat, right? This looks like a shoes, right? So first thing is we're going to normalize our data, and we're going to normalize it because sometimes if we're having like different scales, it could lead to different ranges. It could be very biased. So we want our data to be in the same range between 0 and 1. This is why generally we do data normalization on our data. As you can see, it's just like a division by 255. Because as we said, each pixel is between 0 and 255. Then we just want to see our images like ankle boot, t-shirt, dresses, sandals, and each image has its label under it. So you can see this is a very typical supervised learning algorithm, which is classification. Next, we're going to build our model. So building the neural network requires configuring the layers of the model, then compiling the model. So first thing is to set up the layers. Well, to set up our layers, we're going to build a model which is Keras sequential. This is a very typical way to build a model in Keras in TensorFlow. First, we're going to flatten our data. We have an input of 88 by 28 by 28. And then we're going to have a dense layer, which is in 128. We're having an activation again ReLU, which I talked previously about, which is rectified linear unit. And then we're having the dense layer, which is 10. You might probably ask why 10, because we have 10 classes, right? So first of all, we flatten our data, and flattening it, like we have 228 by 28, which is going to have we're going to have an array of 84 pixels. Sorry. Okay. Next, we're going to compile the model. So first thing, a model in what is a model in TensorFlow? Model in TensorFlow groups layers into an object with learning and inference features. Okay, and each model has different attributes, different methods, sorry, like compile, which configures the model for training, like the optimization, the loss, the metrics, and so on and so forth. For example, here we have the compile method, which has the optimizer Adam. We have the loss function, which is sparse categorical cross entropy, and we have the metric, which is accuracy. So first thing, after having your model, after compiling your model, next thing is to train your model. And how are we going to train the model? We're going to fit the model. We're going to actually to fit the model. And how do we do that? Well, basically in TensorFlow, when we say fit the model, is going to feed the data into the model. So we're going to feed the model the data that we have, right? And here, as you can see, we have 10 epochs, very small number of epochs, because normally it's like more than 500 epochs to say, for example, if an image is good or if a model is good or not. But here we can see that we have a loss of 0.2 and accuracy of 0.9, which is really great actually, which means that the model has learned from our data set. Then we're going to evaluate our model, because while we talked about the machine learning workflow, we said you have your data, you have your model, you train your model, you get an accuracy. This is the accuracy that we got after all, after training the model. And now it's not clear if, okay, the model has trained, but we are not sure if it memorized everything or generalized on our data. And what we want to know is the accuracy of the test images. And test images are images that he didn't see before. They could be from the data. Generally, they are from the data set. So it's like you're having your data set and you split it on 18% for your training and 20% for your testing. Okay. So here we have a test accuracy of 0.8, which is not not bad at all. So if we're going to see now, we're going to say that our model did learn, so it does not have underfitting, and the test accuracy is high, so we're going to say it did not do overfitting generally. So next we're going to make some predictions, and this is typically using like TIFF Keras sequential, the probability model. You're having your model, and then you predict on test images. And the prediction is pretty straightforward, as you can see. It's like you have arrays with different numbers, and these 10 numbers represent the model's confidence that the image corresponds to each of the 10 different articles of clothing. So, for example, prediction of 0, how's the probability or the confidence that this article could be in one of these 10 categories? As we can see here, the prediction is 9. So, what the class hour of the first article is 9. Okay. This is basically a graph for like 10 or more different like subplots. So for example, this is the test data that we have an ankle boot, and the one that he has used is they has resulted in is 9. And you can see also the same that this is a sandal with 89% a sneaker, which is sneaker. So the model did somehow learn, but it did make some kind of mistakes after all. And this this tutorial, as I said before, you can find it on tensorflow.org. And now I'm going to go to see all your questions. If you have any, please ask some questions in the live chat so that I can answer them. I hope somehow everything was somehow clear. But if you have any other question concerning computer vision, learning resources, or anything, please ask them so that I can answer them. No questions? Okay, one question is, how do we choose the hyperparameters for CNN? Well, basically for CNN, there is like uh, a set of like hyperparameters generally that are used, like the optimizer is generally Adam, activation function is generally rectifies linear units. But then you can start, for example, like I said before, you can see the C code, some code, for example, for object detection, you can use the efficient det, and then see the parameters that they have used and train your model and do an inference, for your model. If the model has good results on your image data, on your data set, that's good. If it's not, then you're going to change the hyperparameters. And you can it's very intuitive. There is no rule for how to choose the hyperparameters. But generally, like I said, it's like you have like um, Adam for optimizer, accuracy as a matrix, and then you have I don't know, 100 epochs or more. And it depends actually if you're having small data sets or big data sets. The batch size also differs, the input size differs. So it's not the same when you're using like, I don't know, 100 pixel image from 1000 to 1000 pixel image. And it depends. So yeah, you need to play with your hyperparameters to get the set that you want to have. But generally, there are ones that people have used and they found that they are pretty useful and pretty accurate. So I advise you to go see them on their papers and try to find if the paper has what are the hyperparameters that they have chosen for more or less like same task. Okay. So another question is why we applied math in artificial intelligence. Well, all the functions are mathematical functions. If, for example, in a very basic machine learning, uh, like machine learning algorithm, uh, a linear function or a nothing function is a mathematical function after all. First, when machine learning started, they only used to fit the data using linear functions, but then they did, everything is very complex. So you need more advanced and more complex modelization, mathematical modelization of your data. So yeah, everything is related to math. Even when you do your optimization, optimization is like a basic gradient descent, like function, and gradient descent is like you're trying to find the global minimum of your function, and all of this is using math. So basically, machine learning is based on math. Okay. So can you please give an example with real data to explain the convolution? Um, what do you mean explain the convolution? Okay, let's try to see. You're having, for example, mm, well, the basic one is like you're having cats and dogs, and you want to try to classify them. So first thing is that you have your data. This data is you have different classes. Basically, most importantly is to have the same number of images of cats and the same images of dogs, so that you can have like so that your data could be balanced. That, for example, your data is fed to the model, and a basic model is a CNN. So as I said, you have like your convolution, your pooling layer, and then you have your activation layer, and this block is going to be repeated. So first convolution is that when we do convolution, we're going to extract the features from the image. The features, for example, for the cat, it could be the rounds of the eyes, how the ears are shaped, and all these kind of things. Even though also it's the same thing for the dogs. Another thing is, after having this convolution, you're going to have a feature map, and this feature map is very like big. Well, it depends on the image, right? But this generally, we want to use pooling layers to reduce the dimensionality of this feature map, so that we can like squeeze the position and don't have the position issue for an image. Another way also to have like to reduce this bias of position is by adding data augmentation. Because when you add data augmentation, you're going, for example, to do a flip or a rotation for your images, and if this the model is going to be unvariable somehow, unvariance somehow for all these kind of images. I'm not sure if I have like answered your questions or not, but typically this is how a convolution can work. So basically, convolution is just a mathematical operation. It's just like you're having two signals and two functions, and you're trying to map out the activation of that pixel and of or that signal. Okay, so what's the best NNN architecture for image processing? Well, image processing, I've never seen, as long as I know, for image processing using natural language, like neural networks, sorry. So uh, for me, it would be like more of this. If you're doing image processing, you're going to use like mathematical operation. You just need to use, for example, OpenCV, which is a very popular Python library that can do image processing for you. There is also augmentations or image augmentations if you're really to do like data augmentation on your NumPy functions. And there is, of course, like TensorFlow has in its APIs, there is a dataset API in TensorFlow that you can use it to do image processing. But an architecture for example, for different kind of tasks for computer vision, it depends. Like I said, for example, for object detection, the best one right now is the efficient. See, there is in the paperswithcode.com, you can see the code, and you can like dive in the paper there. Okay, and there is a question is, what is the problem of having many hidden layers? Will the CNN learn better? Well, um, it depends actually of your data. Like, for example, if you're having a data which has lots of, I don't know, lots of complexity in it, lots of objects in it. For example, one in a very typical New York road or New York street, as you can see, there is lots of buildings and lots of things there. And if you're trying, for example, to detect, I don't know, like small something, it's very important to have like more layers, because your model won't be able to understand the complexity of the image. But if, for example, you're having a I don't know, a cow or a cat or a dog in a I don't know, like could be, for example, in an empty road where there is no one, or just like in the image I showed before, it could be very easily identified because you have one object in a whole image. So it's like the CNN is going to only look for that object and know the activation signals are there. So he's going to try to get that object. So there is no problem of having very too much of hidden layers, but and it depends actually on the task and the problematic. It could be good and it could be bad depending on the task and depending on the image. So will this cause the vanishing gradient? You mean the vanishing gradient for the many hidden layers? Well, it could be. It could be. There's a problem there. Yeah, so it could be. There is another question. Do we have to use the fractal algorithm in the image processing process in this case? Mm, well, uh, uh, the fractal algorithm, I don't, well, I'm not sure really. So I'm not sure. I'm really not sure. So I'm not going to answer that question. Another question is, do we have to use the digital linear filter algorithm in the image processing process in this case? What do you mean by digital linear filter? They, can you please explain the digital linear filter? Then, are there any other questions? Okay, there is one. CNN for generating numbers from an image. Do you know a framework to get an image from numbers? Well, basically, CNNs not just generate numbers. Like CNNs, okay, images are represented in numbers. And to get the insight from this image, and by insights I mean object detection, or image classification or any other task. So basically, CNN is just a model or a mathematical function that can be used to generate insights from images which are numbers. But if you want, for example, you have your input, you're going to get an image, you're going to get an image, and from this image, you're going again to generate an image, which is like using pill or using I don't know, any other. There are quite ones to like generate images from numbers, like pill, pillow, which is in Python. There is also scikit-learn. I think also has this function. So it's like a function. You're going to have like a function, and this function is going to convert the numpy array that you have into an image. Okay. I'm not sure if this answered your question or not, but another question is, will the residual neural network ResNet solve this problem? Um, Generally, yes. ResNets are used to have like this vanishing gradient, because that's typically a problem when you have, for example, uh, big weights, and these weights tend to at a certain level tend to come too near to the, not the weights, but tend the, like the gradient tends to the to come to near the zero. So when we're using ResNets, you're going to skip certain connections, and you're going to avoid multiplying weights and then dividing by in the gradient, and then you're going to avoid the gradient panel, the gradient kind of vanishing problem. Okay. Yeah. Typically, well, typically these are like, if you're interested to know more about, you can see like tensorflow.org or any other kind of I don't know, like Coursera or Udacity, that you can learn from. It can be typically computer vision, natural language processing, or any other kind of task in like machine learning or AI. Uh, okay, so so someone um, do we have to use the digital linear filter algorithm or preset preset functions in the programming language used in image processing process in this case? Well, image processing is just, you're just going to, it depends on what kind of processing you want to do. For if you're going to do image processing, generally when you do image processing, you do it using Python libraries. I've never heard about digital linear filter, so I'm not sure about it, but perhaps it can work, perhaps it does not work. But generally, when you're using like programming, like processing in the image, you do this with Python libraries, with OpenCV. You can do it with NumPy, or you even can do it with Keras in TensorFlow. I'm not sure if this answered your questions. Okay, I'm going to answer one last question. Why do we use the dropout layers in CNNs? Because sometimes CNNs tend to be very complex, and this complexity can can harm more and make the model like memorize every part of your image, and we don't want it to overfit. We don't want our model to memorize the data. So what we use is we use regularization techniques to have like somehow like reduce the complexity of the model so that we can have like a trainable model which generalize, not memorize. And this using like regularization techniques. One of them is dropout. So basically, there are lots of other regularization techniques that we can use, and it depends on the task and it depends on the project. But dropout tends to be very good and give great results. So I think with this, we can like wrap up here. Thank you very much for joining us. This is the last session for today. And with that, I want to thank you for joining us. And please do join us for the up 16 other weeks. And please stay safe. Thank you very much. Bye bye.